Hello friends, we have started with the photo detector. Okay, right? And if you want to design a photo detector, what are the parameters are normally important to design the photo detector? These we have already discussed. Some parameters we have discussed in the last class. Okay, so one of the parameters this I will discuss today. Okay, so response time. One is the response time. By name the response time, you can understand that response time is how the device can respond. Okay, how the device can respond. Okay, how much time required to respond by the device. Okay, how much time is required to respond by the device. Okay, so normally in the photo detector, photo detector means this is a diode, photodiode, which is used to convert the electrical signal to the light signal to the electrical signal. Okay, so that means the light signal. This is a one kind of the you can consider as a pulse signal. Okay, suppose here you can see the light signal. There is a pulse. Okay, so you can see the pulse. So you can see that this is the turn off time. The light is off and then the light is on, like this way. Light on and then light is off. So when light is off, then zero light intensity. When light is on, there is a higher intensity of the light. Okay. So the moment there is a transition between this turn on to turn off, this moment, okay, this moment should be very fast. Okay, that means your response time is very much less. The speed is more. Okay, so that means if the detector has the less response time, that means the speed is more. Okay, less response time means it require too much time to respond, and the speed will be less. This is not be suitable for optical communication or any other sensing application, right? So the response time is also important if you are going to design the photo detector. Okay, so suppose according to this light signal, you are getting this optical signal. So this difference, this one. So what is this one? So the light is going to, so when you are giving the light, so electrical signal you should get. So it is going to increase and it will reach to the maximum intensity. It will reach to the maximum electrical value, right? So this is the 10% of the maximum value. This is the 90% of the maximum value. So these, if this is very small, then you can consider as the response time is very the response time, the value is very less. That means the speed of response, speed of the detector is high. Okay, so these our aim is to achieve to reduce these things. Okay, to reduce this value. Suppose this will be nanosecond like that or microsecond like that. If it is millisecond or second, that means to according if you convert this into speed, the speed will be very less. Okay, before nanosecond and microsecond, you will get the gigahertz, megahertz response, right? So this is the response time. So how much time is required? The measurement time between the 10% of the maximum value to the 90% of the maximum value. So this value should be very less. So it depends on the response time depends on the material properties as well, right? So there is one parameter that is called the capacitor, the load resistance, and the design of the capacitor means if we are going to design a photodiode, there will be a capacitive effect. So there is a anode, there is a cathode, in between there will be multiple layers. So it will be as a capacitor also. So we need to reduce the so tau is equal to normally the response time is equal to tau is equal to RC. Okay, if you need to reduce the tau response time, you need to reduce the C as well as the R also. Both you have to reduce the resistance of the device. Both you have to reduce. So when you're going to connect the load resistance also, the load resistance value will be very much less. And the capacitance that also depends on the how you are going to design the device. The design of the photodiode is indirectly influence the response time. It first influence the capacitor and then it influence the response time. So if you are using the high thickness device also, it will directly impact on the it will impact on the capacitor, which in turn it will change the response time. So there are the some other different factors are important for going to fabricate the capacitor, and if you measure, so then you can compare, you can evaluate the how what are the main design parameters that they are which influence the capacitor and as well as the response time. Now come to the pin photodiode. Okay, so pin photodiode by name, there are the three layers. One is the P layer, another is the intrinsic layer, another is the N layer. Okay, normally for design the PN junction diode, the PN junction diode is there. So there is one junction. Okay, you need to prepare the hetero junction. Okay, the hetero junction like that, so that you can achieve the good photodiode. Okay, you know also the photodiode, we have to apply the reverse bias for the photodiode. Okay, so now the PN junction diode is there. So normally what we have to do, we have to increase the internal electric field. Okay, we have to increase the internal electric field for that, right? So how can you achieve the internal electric field? We are giving the device can get the electric field from the reverse bias also. Huh. And from the but the reverse bias, if I give the more reverse bias, that is also not suitable. Okay, better to better to induce the high internal electric field for dissociating the electron hole pair, because in photodiode first the lighting incident, the electron hole pair will generate, and this electron hole pair will be bounded into the device. We have to dissociate the electron hole pair, and then only the free carrier will generate it, which will be come into the outer, external circuit. Okay, so this PN junction diode, that will be the electron hole pair should be separated very easily. So in order to increase the dissociation rate, PN photodiode is also developed, which can indirectly, which can provide the high efficiency as well, right? So normally the one is intrinsic layer, that will be inserted between the P and region. Okay, this intrinsic layer, this is very much likely to. We know that the likelihood region, we can get the wider depletion region as compared to the highly doped region. We can get the narrow depletion region, and the likelihood region we can get the wider depletion region. Okay, so then the intrinsic photon energy, that will be this is the one factor that we are going to implement one intrinsic layer. So if the depletion region is wider, so we know that during insert depletion region we can achieve the electric field, right? If depletion region is wider, so we can achieve the electric field, and in the depletion region there will be the no other majority here. Whatever electron hole pair will generated, those will be easily distributed by the electric field, the high electric field, and those can be easily collected by the external circuit, and there will be less chance of the recombination, because as there are no extra electron hole pair. Okay, so this is the phenomenon will increase, responsible for increasing the current as well as the efficiency of the photodiode. Okay, that's why the pin photodiode is there. So in this diagram, you can see the structure. Okay, so the intrinsic layer, you can see, suppose the due to the intrinsic layer, the depletion region will also wider. You can see this the highly doped, the narrow depletion region. Here will be the higher depletion region. Here will, and due to that also this junction, there will be the wider depletion region, and this will be narrow depletion region. So that means that you can consider that the entire intrinsic region is converted into the depletion region. So that means the wider region is there, electrical present in the wider region as compared to the PN junction diode. Right? You can connect the load resistance and the bias voltage for getting the current. So here is the Venn diagram. Now, as the higher electric field, there will be the higher band bending. Okay, so the electron hole pair will generate lots of electron hole. So normally electron hole pair will generate in the entire region, P region, intrinsic region, and the N region also, right? But the P region and the far end of the intrinsic layer, right? The P region and N region. So there are the other free carrier also. Okay, sometimes in the reverse bias also there will be some peak areas. So whatever electron hole pair will produce, those electron hole pair, suppose a hole is there, the electron is there. So this is the bounded. Okay, this is try to diffuse towards the junction layer. So there will be a diffusion lifetime. Okay, so if it is not dissociated, after some time this electron will be come into the ground state and it will be recombined. Okay, so before recombining the with the help of the electric field, this electron pair should be separated out. Okay, so but in the whatever electron pair will produce in the intrinsic region, lots of electron pair can produce in the diffusion, and all the electron pair will be responsible for dissociation because where higher electric field is there, so the those electric field will be responsible for separating the electron pair, right? And as there are no other electrons here, no other holes here, so this electron can easily transfer towards the end region and will be collected by the external circuit. This hole will be easily transferred towards the P region and easily collected by the external circuit. And we know that to for generating the electron hole pair, the whatever light intensity you are giving to the photodiode, this light intensity energy should be greater than the band gap of the PN junction diode. This is the main criteria for estimating any photodiode device. So in every photodiode there will be one photovoltaic mode, one is the photoconductive mode. Normally in photovoltaic mode we are not going to provide any bias voltage. So whatever electron hole pair will be produced, so this is the device. The hole will be reside into the one end of the PN junction there. PN junction semiconductor electron will be reside on the other end of the end. So these will provide a potential. Okay, so for that we can which can be used for the solar cell. And so if you want to see the output current versus input graph, output current versus input graph, so you can see the ratio of the output to input is very less. So that will be normally used for the generating the solar cell voltage or solar cell, okay, power, which will provide the power. The photoconductor mode mainly used for optical communication and sensing application. Photoconductive mode. That means you are applying the reverse bias so that hole will come out from the device and electron will come out from the device. It will produce a higher current, and due to the reverse bias also there will be the acceleration of the hole and electron will be very much high, so that the will get the fast response for photoconductive mode. Okay, so there are the two parameters of the diffusion length and the kinetic. Both are interrelated. Diffusion length means suppose the electron, so suppose the electron and hole, the electron hole pair. So there will be a diffusion length. Suppose means it is diffusing toward the other one side. Okay, after some time, so it is moving towards the one side. After some time, this electron will be come back to the ground state. Okay, the recombination. This called the recombination. So that this is called, so this length. So how after going to some distance, it will come back to the ground state. This length is the diffusion length. So before coming to the ground state, these electron molecules should be dissociated. So based on the diffusion length, we can determine the thickness of the P type material or N type material, and the junction region where the junction region should be present in this thing. If the diffusion length is high, that means carrier lifetime is also um, high. If diffusion length is less, the carrier lifetime is the time required to recombine the electron hole pair. Okay, this is the carrier lifetime. So both are directly proportional. Alright, so there is a formula you can see that the L is equal to the root under dn by on the diffusion coefficient, there's the lifetime, carrier lifetime is the diffusion life. So that means if the material, so the material property also depends on the diffusion length that relates to the material property. Suppose you are going to use the one material which has the high diffusion length the electron, so we have to choose those material for exhibiting the photodiode or being photodiode like that. So here you can see these are the some diode, photodiode, the pin photodiode, the silicon photodiode, gallium arsenide, germanium photodiode. you can see the higher wavelength, the optical absorption coefficient is going to be reduced. Okay, the lower wavelength, you can see higher optical coefficient. So higher optical coefficient means it has capability to absorb more amount of the photon. If more amount of the photon absorbed, whatever light are you going to incident. So if all the lights are absorbed by the device, so we'll get a faster explosion, the higher efficiency. Okay, so next class I'll discuss the avalanche photodiode. So thank you, and please like, share, and subscribe my